This video provides an overview of the mechanical interface details needed for a successful Lepton design. There's one option when it comes to mounting Lepton to a PCBA, the MOLEX Socket connector, available on DigiKey or Mouser. You cannot reflow the Lepton, since the high temperatures will damage internal and external components. It's important to note that only the socket itself goes through the SMT process. There are a couple of different part numbers and variations for this socket. Generally, the spring retention model is the one used most. It keeps the Lepton from falling out of the socket, but it does not necessarily keep the Lepton seated in the case of a significant physical shock. So it's important that design is done to make sure the Lepton is always compressed within the socket. The orientation of Lepton is important too. The socket has notches that accommodate the shutter clips and align the Lepton. Mount the socket with notch A on the top horizontal side to provide landscape orientation. For portrait orientation, rotate the camera 90 degrees. Portrait orientation works better for applications like smartphones and other vertical displays. Mount the socket with notch A on the right vertical side, as shown in the slide. Inserting Lepton into the MOLEX socket is relatively easy, but it's important to do so carefully in a controlled manner. The best method is to use a tool that provides a consistent, even force to press the Lepton into the socket. Avoiding any sort of concentrated or pinpointed pressure areas on the shutter is important. The Lepton is MSL1 and should be handled in clean conditions to prevent dust and debris. Secure the Lepton with no more than 2.5 kilograms of force. When properly seated, the shutter tabs are nearly contacting the MOLEX socket. If they're not making sufficient contact, or are not parallel, it's not fully seated. Properly seating Lepton is the first step, but keeping it in place is equally important. Use a Poron foam gasket to maintain mounting pressure on the camera in the final design. Be careful removing the Lepton from the socket. Apply pressure inward only to the shutter clip sides and pull from the socket. Avoid grasping and pulling from the non-shutter clip sides. The shutter is fragile, and the support clips can break. Replacement Lepton shutters are not sold separately, since the Lepton and shutter are calibrated together. Keep thermal design in mind when integrating Lepton. Lepton cannot perform properly at temperatures greater than 60 degrees Celsius. Although the sensor will be operational, it will not meet its optimal performance and the radiometric accuracy will be degraded. It's important to have isothermal conditions for the camera to help achieve the highest radiometric accuracy and best image uniformity. Keep heat-generating high-power components away from the Lepton. Minimize the temperature delta across the Lepton to optimize radiometric performance. Take the field of view into consideration when designing Lepton into your system. Be sure to review the mechanical IDDs as well as the CAD files. The window and the cutout inside the window need to be large enough to accommodate worst-case tolerance stacking and prevent vignetting. It is important to note that Lepton does not have perfect Boresight accuracy, so it's imperative to take that into account when designing Lepton with other sensors that may need to be aligned. Do a mechanical alignment or software alignment process that can handle up to 5 or 6 degrees of Boresight variation. A window is essential to any design using Lepton to protect it from impact, dust, or liquid. The most typical window used is a 0.5 millimeter thick DLC coated silicone window. It's a durable, effective, and less expensive solution for this camera. Transmissivity of the window should be at least 75% to help with radiometric accuracy compensation and overall image quality. Higher cost germanium windows with an anti-reflective coating have the highest transmission and are chosen for optimal performance. Here are 2 Lepton assembly stack methods. The key difference is the component compressing the Lepton into the socket. On the left, the window is providing the compression, supported by the frame of the device. On the right, a bracket with a clip is pushing the Lepton into place. A bracket is generally more convenient because once the Lepton is in position, it's easy to immediately install the bracket over it. The shutter is an integral part of the Lepton camera module too. Take steps not to hinder its operation. A broken or non-operating shutter will cause the camera's radiometric functions and non-uniformity correction to stop working, so avoid putting pressure on the aperture and the area circled in red to prevent jamming the shutter. Poron foam is a pliant material that can press the lepton into its socket without putting uneven pressure on one single part of the shutter. It also provides a margin for error in the mechanical stack-up of the system design. A cutout of the Poron foam is available in a step file upon request. The addition of the foam is the second most common way to damage a lepton. Be careful not to let it obstruct the mechanical pins and shutter mechanisms. And apply adhesives carefully. Any excess glue or debris will cause the shutter to fail. Use approximately 1 kilogram of force to safely secure the lepton and prevent it from being knocked loose from the socket. Make sure compression of the Poron foam falls within the parameters of the linear region of its deflection curve. This provides the maximum amount of tolerance for mechanical tolerance error, as well as a repeatable amount of pressure to hold the lepton in place. For further questions, mechanical drawings, CAD, or support in general, please go to www.FLIR.custhelp.com to connect with our support agents, as well as our applications engineers. Additional integration resources can be found at www.FLIR.com/lepton integration. Thank you for your time.